welcome guys for this last talk. So this talk is going to differ a bit from what we've seen yesterday. I'm going to introduce a kind of new topics here, much more closely to the hardware. So putting a bit of context here. So for those who don't know me, I hadn't had the chance to talk with all of you. So my name is Arthur. I just graduated from EPFL last week, and I did my master thesis in a startup which is called Quantum Machines, which you can see here, the logo. And basically, I did 1 full year as a master project in Quantum Machines, and I had opportunity to learn a bunch of stuff regarding the quantum computing stack overall. And more specifically, potential applications that we could carry using their stack. And it turns out that the very good relationship we have with Quantum Machines today allowed us to basically sponsor this event, which made everything free for you guys. And we're super happy that they enabled us to realize this event. So I would like to deeply thank all my colleagues at Quantum Machines, and we hope to have much more collaborations in the future. So, okay, so here, nothing new. So now I will shift towards what my thesis was about. The question that was raised is, so as Giuseppe mentioned yesterday, we have lots of algorithms that try to cope with noisy quantum hardware. We have hardware today which is still kind of imperfect. And of course, we expect that imperfection will stay around for a while. But there are many topics that quantum computing tries to address to make sure that we can leverage all the power required to do so. And what I'm going to present right now is the result of my work that I've been doing over there. So it's basically my master thesis here will be kind of attending that I hold last week. And it's actually pretty cool because it compensates with the fact that last week I was all alone with my professor in one room. So now I get to have a real thesis. So it's pretty nice. So yeah, so the topic of today, so first maybe to give a kind of a tribute to all my colleagues here. So to present a bit the team at Quantum Machines. So Quantum Machines is a startup based in Israel, in Tel Aviv, and actually employs all over the world. We have people in the US now. We have some people in France, some people in Switzerland, me, and currently people in the UK and Germany as well. And of course, the team is growing. To give you an idea, when I started at Quantum Machines last year, so the company is 3 years old, we were 24, and today we're 65. So in 1 year, we encountered an exponential growth, so which is pretty cool and pretty exciting because you meet very talented people. And so here's a bunch of the backgrounds that you could see, and we basically have people, physicists and computer scientists and engineers that come from very different backgrounds who worked on the very different technologies, more specifically hardware technologies. And I will explain now how it is relevant for the Quantum Orchestration Platform, which is the device, the structure that Quantum Machines is developing for enhancing quantum control. Okay, so the agenda for today, I will not cover, of course, everything in my thesis because it would summarize like 60 pages, so I will spare you that. And especially after lunch, we feel kind of heavy, so I'll try to keep you awake as much as possible. But basically, I want to give you an idea of what are the challenges occurring with quantum control, and more specifically by introducing the Quantum Orchestration Platform, what it consists in, what are its basic features. And then we're going to go, of course, of the use case of the weekend, which is variational quantum algorithms, which now you know by heart, right? You're expert in this. So we're going to see how the pulse control and the real-time capabilities, and I will explain what real-time means in a second, could potentially enhance the capabilities of this platform. And finally, the third point I wanted to make, and this is actually where I hope the research will be conducting in the next few years, and there are actually a very nice proposal talking about this right now, is how we can use the low-level expression of algorithms using the pulse-level language. So to make an analogy here with what Julien presented yesterday, this would correspond to Qiskit Pulse, Qiskit Runtime, so all the modules that would go a bit down the stack. And exploiting all of this structure could actually enable much more interesting applications, and more specifically using quantum optimal control theory. Okay, so now going through a bit of what we call about controlling quantum systems. So during the past hours, you've been dealing essentially with quantum gates, right? So you have the conception of what is a Hadamard, what is a phase gate, what is a C-naught. But actually in hardware, it's not quite clear what it is, right? Usually when you take your phone, for example, the signal or the computer, the signal that you send towards the hardware is actually electric signal. This is why you need batteries, and the electric signals and what goes through the transistors are what enables you to transmit and and acquire information from your hardware. So you have acquisition of data, right? You pick something from the screen, and you also send data by typing something on the keyboard, for example. In the quantum world, the idea is still the same, right? We have to be able to probe the quantum processing unit, which I will summarize as QPU from now on, because this is usually what we will call like our ensemble of qubits. And there are many, many different platforms to do this. So the challenge of quantum machines, what it steps into is how can we ensure an efficient quantum control strategy for many qubit platforms. So for this, as I mentioned, language of control in the quantum world are pulses, electromagnetic pulses. So we're dealing with light here, and we'll see that there are very specific features that should be aligned to this light. And of course, this is to control, but we also have to sample out results, right? What we called the readout. When we say measurement, actually, it's very easy how you can write a circuit and say, I will measure, but what does that actually mean? It's also a very deep question, which I find really interesting, philosophically speaking, collapsing the wave function, but this is not the purpose of this talk, but I could talk about this for hours. And for that, as we are classical human beings, we're not quantum behaving, right? So we cannot probe the superpositions. We have to probe classically the device. So we have to develop some kind of classical infrastructure, which will symbolize some kind of nice orchestra. So I don't know if you've been in an experimental lab. I know some of you work in experimental labs, so you have usually lots of nice devices which enable you to perform this control and these characterizations. And you would expect that, yeah, you know, everything is sorted out perfectly. You have one communication forwards, one communication backwards. But in reality, it's a bit more uglier than that, usually. Like, you have a bunch of devices that are required to, sorry, just a second. Yeah, you need a bunch of devices that enable you to perform those controls. So here's a bunch of them. I won't go through it, but maybe worth mentioning what an AWG is. AWG stands for Arbitrary Waveform Generator. And this is usually some kind of big device that will be able to generate analog pulses, the waveforms that you will send towards the device. And depending on the nature and the characteristic of the waveform, you will be able to actually compute a quantum gate. And we'll see that the characteristics of your pulse, when you choose them specifically, this allows you to perform a specific qubit rotation or maybe a 2-qubit gate. So. All right. So yeah, so those set of tools, usually AWGs, digitizers, lock-ins, all of those that you would require in a lab, they were perfectly fine when we had QPUs that were composed of maybe 3, 4, 5 qubits, which we were not so long ago, right? And actually, if you take a look at all experimental labs in the world, in the academic world, most of them are trying to improve the quality of the qubits. And this is actually like the basis of customer of quantum machines. It's people who are trying to build better and better qubits. So they don't need like to scale. They're interested in building the most efficient qubit ever, extending the coherence times, making sure that they are resilient against noisy processes. The gates that you compute on them are carrying high fidelity. So that works. But what happens now? Like we mentioned it yesterday, IBM has just announced this new processor containing more than 100 qubits. And we need more and more control systems to be able to control this quantum processing unit, which is growing bigger. And what happens when we get to the fault-tolerant era, if we have millions of qubits, you can imagine that all the set of devices is not going to scale up well in the lab, or it's going to be like kind of huge. So here's a bunch of experiments related to different quantum platforms. So I won't cover them in details, but this was just to give you an idea of like the increasing complexity of characterizing a device and controlling it when you're considering a specific quantum platform, and also when you're scaling up the number of qubits. So as I said, like this combination carries many inconvenient features, right? So here's this nice image where you imagine in a lab where it's always messy. You see a lot of cables, right? If you have the chance to go see a quantum computer, you have lots of all the cables that come out from the cryostat. It's pretty annoying, and it's a challenge. And usually it would also take time to develop all this setup. Like the money required to build a quantum computer and this control system is actually very expensive. What about like more specific features that allow you to perform more complex experiments? And we'll talk about feedback in a second. Feedback meaning that we want to be able to process the data that we require from the quantum computer and directly re-implement it without having to go back to the client PC to post-process the data in Python, as you're doing with the VQE right now. How can we like leverage the control system to be smarter than that and actually replug a new program according to what it just sampled? And the programming can be very hard, especially at a low level. And this is why we invented the circuit model. It's to ease you the fact that we have many parameters to account for. Okay, so now I will shift towards the presentation of what the concept of the quantum orchestration platform here. So the QOP is a framework that allows you to, that is composed of basically two stacks. You have the hardware and you have the software. So here you see this nicely represented qubit. For that, we have a dedicated hardware, which is in charge of both emitting waveforms, generating them, and also acquiring them. So as another device that I presented to you earlier, you would be able to perform just that with an OP, what we call the OPX, which is the core hardware of quantum machines. And based on this control, we have something which is quite specific to its for a specific usage, which is much smarter than what we have with LWGs. So to give you an idea of why a pulse processor is needed. When you have an AWG, so as I said before, you want to store waveforms, okay? All the waveforms that you will need to apply on your gates, they have to be stored in memory. And usually, experimentalists, they have to do characterization. And this usually goes by sweeping experiments. You have a pulse, okay? And you want to sweep parameters. And with an AWG, usually it is quite cumbersome because you have to store every waveform with every single parameter. And so when you want to do big sweepings, especially 2D, 3D, etc., you end up with huge amount of data to store. And this is not really efficient. Instead of that, the pulse processor here is what makes things much smoother to encode. And the fact that we call this processor is basically because it's based on an FPGA. The fact that you can generate the waveforms and acquire them on top of being able to perform classical control, so you can actually perform calculations in real time and you can do real-time modulation. And the cycle that you require here to do this calculation is at the scale of the nanosecond. So everything happens within the box in the hardware, and you don't have to wait for the client PC to send all the data back and forth, which takes additional latencies, additional runtime, and of course extend your experiment duration. So the pulse processor enables you to do a few things. The first, as I mentioned before, is waveform generation. But now the fact that waveform generation is much more interesting to do with this pulse processor because you are able to parameterize multiple features of this pulse. And this parameterization is dynamic. You can tune it in real time. You don't have to wait to load in memory another waveform. So few characteristics that you can modulate in real time. I will show you an example, but you have typically amplitude of the pulse, duration, the relative phase, its frequency, and many other features that you could tune up in real time. Also, we have waveform acquisition. So as I said, readout is super important. We have to make sure that we are able to do efficient readouts. And of course, you would expect that the quantum processing unit, when you do the measure, you just do 0, 1, right? Like this is what you sample out. You get the counts on Qiskit. It's pretty nice. You get a 0, 1. But what actually comes out of the quantum processing unit is not a 0, 1 answer. It's something analog. It's not digital. And so you have to do some kind of post-processing, some signal integration and demodulation, which allows you to convert an analog signal. Sorry? Oh, okay. By the way, feel free to interrupt me if you have any questions on this topic. You have to transform an analog answer from the quantum processing unit, which you acquire through the OPX, to something digital. this is the step that we call state discrimination. So you give a binary answer, was the qubit in the ground or excited state, based on the signature of the waveform that you will acquire back as a reflected waveform, a reflective waveform that comes back from your system. And on top of that, so this is where the classical processing is useful, is because you can encode many complex calculations in real time. So you reduce the latencies, so you can perform simple calculations, additions, multiplications, of course. And all of this can be done simultaneously. And finally, when you want to do programming languages, and when you want to conduct an experiment, you need what we call control flow. And for you, everyone here knows what is control flow. It's basically tuning your experiments such that you can control where it goes. So you can do loops, you can do if-else statements, you can condition, you can do multiple conditions. We have even switch case. I will show a nice example of switch case later on. So yeah, a bunch of those tools which are necessary if you want to compute complex computations. And when you combine all of this all together, so we have this nice expression at QM, which basically called this embedding the experiment phase space. So meaning that if you are able to combine those four components, you are able to cover a very large range of experiments in your lab. So those range of experiments, this is why I was interested in what can we actually do with the OPX. Can we push the limitations for algorithms? Can we push it for error correction, for characterization experiments? And the answer is all of this. But of course, each of those specific topics requires specific attention, and I will focus later on the challenges that incur with variational quantum algorithms. So here's an idea of what the processor consists in. And to top it all, because we want to make this easy for the user, we wanted to create a programming language, which is easy enough to basically consist in pseudocode. And so we have what we call QA, so it's a pulse level programming language, which allows the user to code very easily their experiments on the QPU and basically state his program, whether it's an algorithm, an experiment you want to run in your lab, characterization, whatever. Everything goes very high level. And this programming language is actually compiled with a specific compiler called XQP and is in charge of plugging in it to the pulse processor and instructing it to modulate in real time given the information. So you can write your program in QA with data that you don't even know yet. Meaning because it's data that you're going to acquire from the QPU. And you can compile it and the compiler will just instruct the pulse processor to react in a certain way with a set of instructions according to certain results. And you can do this control flow in real time, which enables you, as you will see, to do very, very interesting things. Okay, so you've been spending a lot of time programming today, so why not keeping up a bit, introducing a bit of the QA language. So we have as I said before, it's a pulse level programming language. So the pulse level commands are usually the most basic one. So we have two of them. We have play statement and the measure statement. Play is simply, playing a pulse on your qubit. So you have to imagine that the OPX is connected to a bunch of output ports, which are directly connected to a piece component in your hardware, in your quantum processing unit. And this play statement just generates some kind of signal that you pre-configured. Here we call the signal pi, because we want to perform a pi pulse, which might be a X gate, for example, on this quantum element, which we call Q1, QXY. And then we have the measure statement with the readout pulse. So readout is the name of the pulse, and RR stands for readout resonator, and is the piece in the hardware that will be used in the transmon architecture, superconducting qubit architecture, to extract the result of the signal. And then you can also process the data, which I will show just afterwards. General variables, as I said, classical processing. So here you have a very easy way to write classical processing, everything embedded into the QA language. And classical variables can also be used for quantum operations. So here, so remember what I told you before, the pulse processor is able to what we call modulate in real time features of the pulse. Here, those variables are possibly evolving according to some measurements. So it's not predefined in advance. You could declare it in advance, but it could also be tuned up during the experiment. And you can actually tune up the amplitude of the pulse or the duration according to the values that you extract from the program itself. And so this dynamic modulation is pretty efficient because you don't have to reload in memory. So to stop the program, stop the experiment, reload a new waveform to do another pulse. You just have to provide one baseline and you can modulate all the features I mentioned earlier. Here, we also add feedback to this component. So feedback is based on the result of the measurements, right? And here, the very specific example is doing state discrimination. So I won't go too much into the details of measurement because it's kind of more involved. But the idea is that we have an operation that we have to perform on the signal we acquire, which is called demodulation. And based on this demodulation, we are able to extract the information which is stored in the variable I. And we compare this variable I to a certain threshold, which is assumed to be pre-calibrated. And this is how we decide if yes, we measured the qubit in the 0 state, or no, we measured this in the excited state. The ground state and the excited state. Sorry. And finally, control flow. So you have, as I said before, if, else statements, while statements. You have actually a bunch of other ones which are pretty useful when you want to do this program. All right, so how does it work? Very briefly, so here you have to imagine that you have your quantum system. So here is a picture of very different qubit platforms. So here you would recognize like maybe the picture that we all have in mind, right? It's superconducting qubits. Actually, the QPU is standing right there, but you have the cryostat, and then you have the OPX, so the quantum machine device, which is basically connected to this hardware. Here you have other ones, like here you have trapped ions, and here you have neutral atoms, and there are other platforms that actually the same OPX, the same platform, could actually control. So which is also pretty interesting to build some kind of control baseline for everyone. Post-processor is able to tune up, as I said before, so I won't come back to this. And the information that the OPX, because now if you want to scale up your QPUs, you have to centralize your information, right? You have many qubits, so you would require perhaps many OPXs to control your qubits. And everything is centralized in a server backend. So it's pretty similar to what you would imagine like in Qiskit. When you send a job, you send it to the queue. The server is in charge of retrieving the data from the control and sends it back to you. And on top of the layer, you have you, the client PC, who is coding in Python the instructions and receive the data that you want. And in our framework, like the combination of the OPX and the QPU is called the quantum machine. This is like the concept, the abstract concept that we define to basically characterize our quantum hardware system, our experiment. Okay, and on top of it, like you would imagine, having of course multiple programming languages or even multiple frameworks to work in, different layers of abstraction. As I mentioned, Qua is currently a post-level programming language, but you could imagine integrating it with much higher abstractions, circuit level, of course, to not mention it. And I will show you how we can do this very easily. So here is a bunch of examples of frameworks. So you recognize Qiskit, of course. There is Circ. And I will talk about Q-Control a bit later on because they do really, really interesting stuff. And this one is Amazon Bracket, yeah, from AWS.
Quick question.
Yes.
You said that you mainly work on the level of pulses, but this was for superconducting qubits, right?
Sorry,
You work mostly on the level of pulses with Q.
Yes. So, and now I will show, like, the next part is going to be to show how we can get up higher in the stack. Like, from Qua, we can actually code at the gate level very easily.
Okay, and this is what you then use for ions, for instance.
Yeah. Yeah, exactly. So you could imagine doing the same kind of deal for every platform. It's just like every gate that you would define for a cloud provider, for example, you don't really care about the QPU that you are going to run in. Like if you assume that you have a native set of gates, it's up to the compilator to translate it into a set of gates that are runnable, and then the compiler will say, okay, this amounts to sending this pulse to each to this hardware component.
Okay, so you include a compiler in Q.
Yeah. So the compiler in Qua, like the compiler of Qua, like compiles the post-level instructions. But then, like the higher level compilers, for example, I don't know if Bruno is here, but he would be able to tell you that the work on compilation that he does at the circuit level to break down unitaries in a set of elementary quantum gates. This is higher in the stack and is currently not part of Qua. Yeah. This is why like we would get higher in the stack, but it's not the purpose of Qua. Qua is like the baseline to code efficiently experiments and using all the retime features at the same time as you would imagine doing the circuit level.
Okay.
And so very interesting questions because it allows me to keep on what we call,
So you showed like, the ion track system and on the left, like the subtracking system. Why, with the ion track traps, do you kind of use one of the devices to just down convert your signals, or?
Yeah. So yeah. So I think I understand. Yeah.
The second question, so in one device, do you have the modulator in it, or do you have a separate device for that?
Sorry, I didn't get the second one. Can you repeat?
Do you IAQ signals? Do you have a modulation inside?
Yes. Okay. So the module. Okay. For up conversion, typically we exploit another module which is not directly in the OPX. We have another module from a quantum machine stack which is called Octave, and which is in charge of doing this up conversion. So that's for the second answer. And so there are a bunch of tools that you could imagine connecting between the OPX and the hardware itself to be able to do the signal processing specific to your QPU. So everything is the OPX acts as a centralized system for both receiving the instructions, and then all the up conversion or the transformation of the signal that you would need, you could couple it very easily on your specific hardware.
So you also can control the carrier frequency and so on.
Yeah.
You have communication distance to the.
Exactly. Yes, absolutely. So
with iron traps, so how is the connection of these two devices? What's for your
the connection. Oh, you mean on the picture here?
Yeah.
So no, you have to imagine it's not one is connected to this one in this case. It's it would be two OPXs in charge of connecting to different pieces of components. Yeah, it's the image. Yeah, it's a bit confusing, but it's two OPXs connected to the same layer, and then we should connect directly to the hardware components. Great question. Other questions, perhaps, before I keep on? Great, thank you for the questions. Okay, so now the next part is okay, how can we try to get up in the stack and go back to the circuit level? Because you, as quantum software engineers, you want to do a hackathon, you want to perform VQA and that stuff, and for that you need quantum gates, right? And so what I will show you here is basically the fact that you can easily compute quantum gates exactly as you would do before, without having to even account for what's below the stack. But what I will show you later is that we actually, as physicists, could very much engage what's happening at the downside because of the real-time capabilities that could happen. And for multiple subroutines, we could perhaps enhance the performance of our algorithms or experiments, typically for qubit reset. I will explain what it is in a second. And those features are only available when you have real-time feedback available. So at the scale of few nanoseconds. So macros in this case, so I haven't specified it before, so the qual language is actually embedded in Python. So it's a context manager that you open in Python. And the idea of macros is that you want to exploit Python, all the structures, all the nice lists, dictionaries, any kind of structures of Python, which are very high level. You want to exploit all of this to generate the quack code. So how do you do this? One example is using a simile Python function, which we call a macro, which does not contain Python instructions. They actually contain qua instructions. So as you would do when you create any function, usually your code becomes much more generic, much more modular. And so this is why we take the analogy of the Lego here, because you can really separate the components and conceal the complexity behind those functions. So typically the quantum gates, as I mentioned before, the quantum gates are an abstraction layer which basically conceals all the pulses that need to be computed directly on your hardware. But of course, there are still some subtleties related to real-time processing, and now I will show you a bunch of examples of macros. So here, for example, you have the most two basic macros for defining quantum gates, typically. So here I define the two gates. So the RZ gate, which is the rotation around the z-axis of the Bloch sphere, which is actually a command already available in Qua, which is called frame rotation. This is actually how it is computed in IBM devices, for example. It's actually very smart. Frame rotation is just saying, okay, I won't set a pulse to the hardware directly. I will just keep track of the relative phase, because it's a matter of just the phase of the next pulses that are going to be impacting. And based on the phase that I can keep track of memory, I will be able to induce a change of frame and therefore induce a z rotation. On the other hand, the pi over 2 pulse around the x-axis here is directly a pulse, which we usually pre-calibrate. And as you can see here, we call it x90, and you can just play it on the target. And you can also, of course, define macros for measurement. And here is now what I will introduce as qubit active reset. So usually, well, in the past, if you do not benefit from feedback, so if you're not able to directly post-process the data you just sampled from your QPU, and let's say you measured your qubit in the excited state, but then you want to relaunch a new circuit. You always start your circuit in the 0 state, right, for every qubit. Usually, how do you do that when you measured it in the excited state? So one option is to let it decay, right? You know that there is energy relaxation in your qubit, so you just have to wait a bunch of time, and after a while, it will go back to the 0 state. So this is an option, but not very efficient, because what the hardware providers are trying to do is to extend the coherence time. So like the decay, the time it takes for the qubit to decay from 1 to 0 becomes larger and larger. And if you are to repeat the experiment multiple times, you see that the latency that you acquire is going to be much more involved. So we have to find a better solution for this. So one of the most basic one is called a qubit active reset, which is to play a pi pulse. So here, let's break it down for a second. I have this x90, which is a pi over 2. Which I multiply by 2 for the amplitude. So I actually double the amplitude to make a full pi rotation around the x-axis. And so this corresponds to a pi pulse, which I will play on what I call target. This TGT here stands for target. But I will specify it's only if you measure the qubit in the excited state. So the condition here is basically analyzed directly on the threshold. And note that this is calculated directly in the processor. It is not processed in your client PC and you tell it to go back again. So everything is done at ultra low latency. Typically, this scheme takes about 200 or 300 nanoseconds. I can't remember the exact number. Whereas, like to give you an idea, to let the qubit relax on superconducting qubits, now I think the T1 are of the order of a few microseconds. And so usually you want to let like 10 times T1 before like making sure your qubit is in the ground state.
I think we hit the millisecond.
Millisecond in the transport? Really?
Yeah. Indeed, we demonstrated 1 millisecond coherence times.
Look at that. So, so actually, like 1 millisecond that you would like to extend, your program is going to take a long time. Thank you. I didn't know that. Wow, very impressive. Okay, cool. So now we're getting a bit more closer to now that I showed you what I wanted to show you about QA and how the QOP works. Now we're entering in what I did with my thesis. So, what are the possibilities for useful computations? So basically what I try to assess is, depending on the number of qubits, we have different expectations, right, from the hardware. It's clear that in the beginning, when we have from 1 to 10 qubits, it's usually not going to be like what's going to bring us quantum advantage. We're not going to be able to compute a useful algorithm. Of course, you can compute a Dutch algorithm on Qiskit. It's pretty nice, but it's not a problem that you cannot solve in a classical computer at this stage. But what is super important, as I said before, many experimentalists try to increase the quality of the qubits. And for that, we need to be able to have tools for characterizing the quality of our qubits and the quality of our gates. So a bunch of those protocols, I mentioned 2 here, which are becoming like kind of standards. They are called randomized benchmarking and gate set tomography. So those protocols are usually kind of a standard for characterizing the hardware and trying to assess the fidelity of our gates. But the thing is, they carry also computational challenges in the realization, especially when you scale up in number of qubits. 1 qubit randomized benchmarking is actually pretty easy. When you start to scale up to 2 or 3, you have to be a bit more mindful of what you're going to do, because otherwise your experiment is going to take a long time. Gate set tomography also, like I won't spend too much of the details, but it can be quite computationally heavy because you want to characterize many observables. But what interests us today, because this is a theme of the hackathon, it's the Niskira, right? So what we envision in the stage where we're aiming between the Eagle processor, which is 127 qubits, upon perhaps in the next few years 1,000 qubits or 2,000 qubits. This is where we might have something useful to play on. And of course, a bit down the road, we also like to think about fault-tolerant quantum computation, and the majority of the scientists believe that it won't happen unless we have quantum error correction available. And Professor Savonami did present it to you yesterday about a few concepts of quantum error correction. And this is basically a hard requirement for making sure that we'll be able to run the most demanding algorithms in the future. So my thesis was like covering a bit of all those topics. I had a chance to implement and work on those topics for very different applications. So actually, the concatenated cat codes that you see is the implementation that AWS is borrowing. So it's quite different from other implementations. If you have any questions about it, I'd be happy to talk about it later. This won't be the focus of the rest of this talk. I want to basically focus on the NISQ right now and what are the inherent challenges for running those experiments. Okay, so you know very well why we use the hybrid, so I will skip very briefly. Of course, the considerations that we need to account for NISQ devices is that they have limited number of qubits, many errors in the computation, limited connectivity, and the whole idea is to use the classical resources that we have, classical computing, to overcome or compensate those those flaws of quantum information. And the variational quantum algorithms are a subclass of those hybrid algorithms, which involve quantum machine learning. And actually, if you have questions, Suyeon, who is here, has worked extensively on quantum machine learning applications, which is also pretty cool. So as you can see, we cover nearly everything at EPFL, which is pretty exciting. So we hope that we'll get even more progress on this. So VQAs, very briefly. We rely on the variational principle. We know that we want to find the ground state. You want to map basically your problem to a ground state search. And this, you know, right? We have this cost function that we saw yesterday, trying to optimize it, the classical parameters. Nothing new here, just setting down the stone for what comes below. And I'm going to talk right now on one specific algorithm, which is one of the notebooks that you have. Don't know how many covered. Does someone already check the QAOA notebook, perhaps? A few of you. Okay, cool. Nice to see. So I will maybe do a bit of spoil, but you'll see there are plenty of things to implement in Qiskit. So it will be nice exercise. So QAOA is designed for a specific type of problem. So actually, we talked about it yesterday. The good thing, the very interesting thing is that it uses an ANDAT, which is inspired from the ability theorem. Professor Kallio talked about this. And the cost function is mapped to a diagonal cost Hamiltonian, which makes it very easy to compute the gates. The gates are they are very easy to compute for this QAOA. That is really easy to realize at the circuit level. And the canonical problem for this is the max cut. I don't know if you have the time, so I will briefly recap what the max cut is for all of you. So you have a graph. Okay, and you want to find a partition of the nodes. You want to partition it in two, such that the line that will be induced by this separation in two will cross as many edges as possible. So you see you have a bunch of edges or vertices, you call them however you want, and you have a bunch of nodes. And as you can check, like this line which is drawn, like separates in two my set of nodes, right? Each node in my quantum computer will be analogous to a qubit resource, and those edges will actually be the number of edges will be actually calculated in my cost function. So here, let's check. Like this cuts 1, 2, 3, 4, and 5. Of course, you can imagine doing different partitions, and you can convince yourself that this is the cost function associated to this problem classically. So here, xj and xk are classical variables, and you have to map this problem to a quantum computer. So you will do some kind of quantization. And if you do the following quantization, so you replace your classical variables. Yeah.
Do you have examples of what kind of problems correspond to the max cut problem?
Yeah. So I for sure I knew like the relations, but it's so from what I gather, they are. Let me come back to this question afterwards, because like I don't want to say anything wrong right now in the flow, but I will come back to this. But I know there are many applications. I think. No, let me find later this answer. Thank you. Sorry, just to finish what I was saying. So yeah, once you perform this quantization, you can convince yourself that this is the cost Hamiltonian, which is coming from this, and it's all diagonal, proportional to sigma z. Okay. So the algorithm itself is described in the notes, so won't spend too much time here. You have the quantum circuit, which is parameterized by those parameters gamma 1, beta 1, gamma p, beta p. And you have all this classical subroutine surrounding all of this, right? So you have the experiment, you run the quantum circuit, and then you perform the cost function up to evaluation, you do the optimization on your classical computer, and then you optimize back your parameters and send it back to the quantum computer. And so this is the part actually where it gets a bit interesting, because so you have played the same game with VQE. You have to relaunch a new circuit. You have to launch a new execution each time you have a new set of parameters, right? Like this is what you did, I think. When you have a VQE, you have extracted your cost function, you optimize your parameters, and then, okay, now I will recall the quantum computer, send a new job, and go back to my circuit. So this is a problem basically. So because it takes lots of time to reload everything from the client PC, you have to reload all your waveforms, you have to reload all your experiments, and this takes huge amount of time because of what we discussed earlier. So the quantum circuit in Qua. So as you can see on the left, I wrote down the circuit for you. So it's a kind of spoiler for those who haven't completed the notebook, but you can convince yourself that this does the job. You first you put your round of Hadamard gate. By the way, notice maybe something which is interesting though is here I use metaprogramming capabilities. I use Python code. This is a Python for loop. It's not a Qua instruction to generate Qua instructions, because these Rx here are defined as macros, and which eventually lead back to Qua instructions. And so I'm using Python to like unroll my Qua program, which is basically a set of instructions. Or only sent once to the XQP compiler. And so of course, when you code at the circuit level, you don't have to account for what happens here, but if you take a look, the C0 gate here requires the CR gate, which is the IBM native gate, cross resonance, and you can check that this runs the cross resonance gate in this case. Okay, so we're coming back on the challenges of those algorithms. We have first, so I won't talk about this too much, but the existence of barren plateaus. So it's something which is currently under study. We have to understand like what is the structure of the problem we're trying to solve to escape problems of convergence towards the solution that we're aiming for variational quantum algorithms or quantum machine learning programs. This is kind of a recurrent analysis that we have to do. And we have also like hyperparameters of your program, right? Like you don't know how many shots per expectation value you will have to run. Is it dependent on the number of qubits? Is it how many rounds do you need to actually get a good estimate of your cost function? Those are questions. And also how many optimization steps before you reach to a satisfiable solution, if you don't get stuck to a local minima. And also, like depending on the cost function, it can be quite complex classically to compute as well. So of course, like you want to make sure that all the quantum computer is just allowing you to perform simple extractions. But for quantum machine learning, for example, there could be loss functions that involve a bit more computation. And the idea is that you want to parallelize as much as possible without like spending too much time waiting for the next quantum circuit to run. And the accumulation of all those things can lead to considerable run times. So the cost function evaluation. So now, like one of the contributions I try to think of when optimizing the runtime of those circuits is to do the much more classical processing directly on the FPGA. I didn't wait for the results to be sent back to the classical user, to the classical computer, my client PC, to actually compute this and reload it to the program. I will use the same Qua program, I will use the same circuit, and extracting directly in real time the results of my measurement and compute the cost function contribution according to the results I just got. And so I reduce the latency per iteration because I don't need to every time extract my data, calculate the contribution, and come back to my computer. And finally, at some point, we have to perform parameter optimization. So once you have evaluated the cost function, you have to move to the next step and calculate the next parameter stage. And so this is where this line becomes interesting, is this IO1 variable, which stands for input-output variable. So input-output is a nice solution we have in the quantum machine instance in the architecture that allows us to considerably simplify the amount of data we resend back to the computer every time. So as I said before, if you launch a new job, okay, you're supposed to launch a new set of pre-calibrated gates. Let's say like you wanted to reperform your gates, and each parameter supposedly changes the gates that you're computing depending on your ansatz. But actually, if you think about it, the parameters that you send only change a few things in your circuit. It doesn't change the full circuit at all. So you can actually think about optimizing the number of the amount of data that you're sending, and also reducing the latencies. And this is the answer to this. So traditionally, as I said, those parameters involve a new job. So you recompile the job, you make sure that you understand all the lines of your quantum circuit, whereas the structure is still the same, the circuit will be exactly the same. And for each new quantum circuit, you are waiting for the results, you extract it, etc., etc. Now with the input-output variables, we have only one compilation because you have one fixed structure ansatz necessary at the start of the algorithm. The parameters are a bit faster after optimization. And the cost function result is retrieved as a single variable, whereas before you would get the counts. So actually in the notebook of QAOA right now, the function expects you to return the counts of the quantum computer and calculate the cost function based on the counts that you did or the bit strings, calculate this, optimize the parameters, and relaunch the program every time. And another nice thing, as I mentioned before, the importance of maintaining real-time features, active reset, for example, reducing all the latency. You can imagine all the subroutines. Won't spend too much time here, but actually there is a nice interest in refocusing your hardware to make sure it doesn't drift away because in an experimental setup, nothing is perfect. You might have some drift linked to thermalization. So you want to develop subroutines to fight against that, because the algorithm can be quite extensive and it can take many iterations. And so this is done through what we call infinite loop, which is another kind of loop running in hardware at no compilation costs. So here's basically a result of the execution time of running such a core program. So here I only took the part where we consider loading the parameters, playing one single pulse and running it back. So it doesn't take the core time necessary to run a quantum circuit. But you imagine that it's the concatenation of all the durations of the pulses, right? But in this case, as you can see, when you use the I/O variables, the time it takes in seconds is significantly lower than what we would have to do when we relaunch a job, right? And so when you have lots of jobs to iterate and lots of iterations, this can become quite cumbersome, and especially it scales with the number of parameters, because let's say if you are dealing with hundreds and hundreds of qubits, you will have gates to parameterize many parameters, and it will eventually quickly become intractable in terms of runtime. We would expect many, many days. All right, so a quick summary. I think, I'm nearly done. The QAOA in QA benefits from real-time added features. So I'm trying to emphasize this. Real-time state estimation and qubit active resets, the on-the-fly cost function calculation, the execution time, reducing the latency between your classical and quantum resources, and you can think it as a full architecture now. And now the question of research, which is actually open, is can we do more? And so this is really what I would like to pursue, hopefully in my research later, because I think it's quite enthusiastic. It's how can we leverage more pulse control for enhancing the performance of those algorithms. So there was a proposal earlier this year done by a Google team, and what they proposed is basically to, try to come back to a mixing of abstraction layers in the specific case of NISQ devices. I mentioned it in the beginning. The fact that we have NISQ devices and we have current a missing knowledge about what's happening in terms of noisy processes makes us quite vulnerable to data that might not be useful when we acquire it. And there are actually techniques going down at the pulse level, which is called quantum optimal control. We try to mitigate those effects related to noisy quantum hardware. And when you usually go at the circuit level, all of this, and especially the real-time features, are completely forgotten. You don't want to account for that. But in the perspective of focusing on a specific kinds of problem, the question might be, perhaps we can use this knowledge of the hardware. As physicists, we say, okay, I want to focus on my specific implementation. I will focus on a specific problem and try to push my hardware as much as possible to solve this very specific task, which is quite different from the usual universal vision that we have of quantum computing. I have Shor, I have Grover, etc. Yes, but it takes lots of resources and we don't have them right now. So if we want to put a more applied perspective, we have to think about how I will solve concrete problems with my concrete available hardware. And so now I will talk about Q-Control, which is another quantum startup based in Australia, in Sydney. And what they do is essentially working on quantum optimal control theory. They actually are doing quantum optimal control with a bunch of machine learning tools. And they showed quite impressive results using IBM machines, enhancing the performance of few computations by tuning up at the pulse level some optimization processes. And the way I started to think about is how we can insert the QOP proposal into this effort of optimizing the pulse level. And I identified basically two, that was not planned. Yeah. So two distinct things. First is what happens at compile time. So before execution. So here is a bunch of proposals that have been done for actually trying to make sure that when you start your experiment, you are dealing with the optimal pulses that you need for computing your experiment. And then, as I mentioned before, your experiment can last quite some time. You might have drift and some evolutions during the experiment. And so for that, you need real-time adaptive schemes. And we saw that with Qua, it's really easy to adapt subroutines which comply with those real-time requirements. So tracking a prediction, control definition, lookup table. I won't go too much into details into this, but those are very interesting leads to really push the hardware in a specific direction. But of course, it kind of changes the mindset that we have of having quantum gates, very generic ones, which are pre-calibrated, always the same at the beginning of the program. Here in Qua, we could use the real-time pulse level modulation to not overload and rechange the waveform at every experiment, but rather change the parameters dynamically. Here's an example of what has been implemented in as a collaboration between Q-Control and Quantum Machines. It's actually the code is actually available in the Quantum Machines and Q-Control website. So here is what we call a closed loop optimization, and as you can see, we use Qua code here to basically refocus our qubits to the ground state. It's like an extended measure for making sure that you start again in the ground state with high fidelity. So, okay, concluding. I hope that I convinced you that real-time capabilities could be really an added value to what we already have today with the circuit model. And we do not lose all the abstractions that we could get thanks to the meta-programming capability. So Qua is really using all those features to make it a nicely environment for computing. The fact that the QOP is structured both at a software and hardware component makes it super easy to interact in many different experiments, ranging from quantum algorithms to error correction protocols, and of course passing by calibration experiments. This architecture embeds both classical and quantum resources. We have the server, we have the classical resources that we want, and we are still working on optimizing those day to day, and of course the quantum resources that we want to exploit to the best of their abilities. And of course the platform itself enables, and we see it day to day with customers. It's really exciting to see the progress that customers do with this platform to enable new ideas of research. So on that note, thank you very much for your attention. I hope it was interesting. And before going back to the question, and I would basically take a look because the MaxCut has applications, and I say yet to figure this out. But thank you very much. And if you have any questions, you can go then now. All right. So, okay, so it's either like after lunch or like fully dead. Even myself, I hope didn't sound too asleep. But yeah, so again, I would like to thank Quantum Machines for allowing this event to happen. And so this is kind of the contribution that we hope to bring, and we hope that we'll have many more events coming in the future. Yeah.
I didn't quite get what was the added value in going more under the hood with signal. Is it to be able to to better deal with errors or
exactly, yeah. So that's exactly the goal. So again, the fact is that like there is some randomness occurring at the hardware level, which is not very well handled at the high level, because we assume that we have perfect gates. Of course, this is what I said. I explained about variational and all the hybrid algorithms. We compensate the flaws of quantum resources, what happens down there, with classical resources. But we know that we have bottlenecks as well, and we have like some things to adapt. And the thing is, those optimization, this classical optimization, if it is brought down closer to the stack, you gain in execution time. You reduce the execution time to compute those experiments. So getting closer to the FPGA code and really trying to optimize with real-time features, it enables you to not go back and forth between the classical and quantum computer all the time. All right, so if we're done, okay, cool. I think we're just on time. So I guess the next stage is we're gonna go back downstairs and continue hacking. I'm of course here for any questions during the hackathon part. Yeah, don't forget that we have a bunch of TAs here available to answer your questions, and we're gonna hack until 6 p.m. And then 6 p.m. we're gonna end the hackathon and join here again to do a quick feedback section. It's not gonna be a talk, it's gonna be to interact with each other because we are all students, and I have lots of questions for you as well, both in terms of feedback around the event itself and how we could imagine the future for future quantum engineers in Switzerland, etc. On that, thank you, and see you later down there.